Hey guys, so for this video what we're going to be doing is calculating the energy for phase changes or using the heating curve. What you're going to need is a very large amount of information about any given compound that you're doing. So this is all made up. The specific heat of the solids 2.9 joules per gram degree Celsius. Specific heat of the liquids 3.8 joules per gram degree Celsius. You're going to need the enthalpy of fusion, and you're going to need the enthalpy of vaporization. You're also going to need the molar mass. You're going to need to know the freezing point and the boiling point, right? So let's go ahead and start. The problem that I gave you, or that I'm making up, is what if we have 10 grams at negative 14.1 degrees Celsius and we're trying to go to a vapor at 59 degrees Celsius. So let's draw the heating curve for this specific compound. So any heating curve is really going to look like this, right? This is just generic. So this is where we are having something cold, solid, and we're heating it up. This situation is where we're adding heat, and what's happening here? We're converting from a solid to a liquid. The temperature is not rising. Remember, this is temp. And this is energy added. And then when we're here, we are 100% liquid. We're going to heat the liquid, and then we're going to convert the liquid to vapor, and then here we are heating the vapor. So that's what the energy curve is for. So I like to identify where I'm at. So if the boiling point is 47 degrees and the freezing point is 8.1, if I'm starting at negative 14.1, what state am I starting at? So I'm starting at a temperature that's colder than the freezing point. So I'm actually starting down here, right? I'm going to have to heat it up to the freezing point, because my goal is if the boiling point's 47, right? This is the boiling point. This is 47 degrees. And this is the freezing point at negative 8.1, right? So I'm trying to increase it to negative 8.1. I'm going to have to heat up that liquid. I'm going to have to convert it to vapor, and then I'm going to have to take it all the way to my final destination at 59 degrees Celsius. So it looks like I have 1, 2, 3, 4, 5 things that I have to total up. I'm going to have to heat up the liquid, heat up the solid, convert all the solid into liquid. Then I'm going to have to heat up the liquid. Then I'm going to have to convert all the liquid into vapor. Then once it's at vapor, I have to heat it up again. So this is the longest possible scenario that you could get with one of these questions. So let me get another piece of paper here. And let's go ahead and start with what question 1 would be. So let's identify the different stages. So stage 1, I'm heating up a solid. So you know that if you're heating something up and you're heating up a solid, point 1, point 3, and point 5 are all going to need the specific heat capacities, right? Which I forgot to include the specific heat capacity of the gas. Let's make that up. Of the vapor, let's say it's equal to 0.95 joule per gram degree Celsius, right? Okay, so you're going to need these 3 are the specific heat capacities. This is the Q equals M times delta T times C. These 2 use the heat of fusion or the heat of vaporization. So let's go ahead and start with number 1. Number 1, we're going to need Q equals mass times C times delta T. So I know my mass is 10 grams. What's my specific heat capacity? I'm a solid, so I'm going to use the solid specific heat capacity, which is 2.9. I'm not putting units in here because it's a very long problem. And my delta T, how much am I heating up? Well, it's final minus initial. So I'm heating it up to negative 8.1, but I'm starting at negative 14. So final minus initial. Started at negative 14.1. So final minus initial. So this is going to end up being a positive number. So it's going to be positive number 6. So it's really going to be 10 times 2.9 times 6. Which, again, I'm doing this with you guys. You should be doing this with me too. 10 times 2.9 times 6. We get 104.4. And what are the units? This was in joules per gram degrees Celsius. The grams canceled out, the degrees Celsius canceled out, so this is just in joules. Again, I would encourage you to just convert everything to kilojoules right away. And then maybe even highlight, circle, whatever. So this is the answer for my first leg of my journey. Now I need to convert all of that liquid into a gas. Or sorry, I need to convert all that solid into a liquid. That's what number 2 is. So number 2, I'm going to use the equation Q equals my enthalpy of fusion times the number of moles. I don't know how many moles I have, right? That's why we need the molar mass, which is 14.9. So let's do that little math on the side. If it's 14.9 grams per mole, right? And I'm given 10 grams. So it's going to be 10 divided by 14.9. I get 0.671 moles, right? So my enthalpy of fusion is 18.9 kilojoules per mole. So it is 18.9 kilojoules per mole. And I'm going to multiply that by just the 0.67 moles that I have. So the 0.671 moles that I have, I'm going to multiply that by 18.9. Looks like it's 12.68 kilojoules. So now we are essentially right here on our journey. Now we have to heat up a liquid. So what equation are we going to use? We're going to use Q equals mass times C times delta T. So mass, which is 10 times, and what's my C? We're going to be using the liquid version though, right? Because this is, we're heating up a liquid here. So it's 3.8. And my delta T. All right, so I'm at negative 8.1 degrees Celsius here. And I'm trying to get to what? 47. So it's going to be final minus my initial. To go from here to here, you're going from the freezing point to the boiling point. So that's going to be 47 minus 18.1 minus the negative 18.1, which is plus 18 or plus 8.1. So 55.1. So if we multiply 55.1 times 3.8 times 10, we get 2,093 joules, right? Why is it joules? Because our specific heat capacity is in joules per gram degree Celsius. So let's go ahead and just convert that into kilojoules. So it's really 2.09 kilojoules. So again, it's just a good idea to maybe separate them out, box them in, star them, highlight them. So that's only 3 legs of our journey. So where are we at? We are at here, right? So I need to go from this to this, right? I need to convert all of that 47 degree liquid into 47 degree vapor. So for number 4, we use the equation. Heat is the enthalpy of, now it's vaporization, times the moles. We know moles because we did it for another problem, which was 0.671. So Q is going to equal the vaporization, which I made up, which is fun, 11.2 kilojoules per mole. And we're going to multiply that by our 0.671 moles. So 11.2 times 0.671, we get 7.52 kilojoules. So that's for heat, that's for converting all of that boiling point temperature into a vapor. The vapor, converting it all into vapor at boiling point at 47 degrees. Now we just have to heat up that vapor to 59 degrees. So what are we going to use? We're going to use the equation like we had before. Q equals mass times specific heat times delta T. In this situation, mass is still the same. Specific heat, which one am I going to use? I'm going to use the specific heat of vapor, which is 0.95 joule per gram degree Celsius in this case, right? And my change in temperature, well, I'm going from 47 to 59. We can do that one in our heads. We're going to increase it by 12 degrees, right? So 12 times 0.95 times 10, that's going to be 114 joules, which is the same thing as 0.114 kilojoules. So to do the whole thing, we're going to have to add them all together. We're going to have to add the first leg of our journey, second, third, fourth, and fifth. So it's really going to be 0.104, sorry, that's a 0, plus 12.68 plus 2.09 plus 7.52 plus 0.114. These are all in kilojoules, right? So our answer is going to be in kilojoules. So the final answer is we got an answer of 22.5. To increase just 10 grams of this stuff from a frozen solid that is below the freezing point all the way to a heated vapor. I hope this helped everybody out. Thanks.